Hey everyone, and welcome to The Explainer. Today, we are going to completely demystify number theory, and I'll show you exactly how understanding the DNA of numbers unlocks these amazing real-world cheat codes for everyday problems. You know, if you've ever looked at a math problem and thought it just looked like a random jumble of digits, trust me, you are definitely not alone. But here's the secret. Numbers actually have a hidden structure. They have this underlying anatomy that makes them totally predictable and incredibly useful. And once you learn how to read that structure, well, math stops being a chore and actually becomes a puzzle you can easily solve. Let's get into it. So, here's our game plan for today. We're going to cover 1. The DNA of numbers, 2. Divisibility cheat codes, 3. Breaking down prime factorization, 4. Mastering HCF and LCM, and finally 5. Solving real-world puzzles. All right, let's jump right into section 1, the DNA of numbers. Okay, let's get down to the absolute fundamentals. We've got to separate factors and multiples right out of the gate. Because honestly, confusing these two is probably the #1 mistake people make. So think of factors as your limited building blocks. They divide a number perfectly, leaving absolutely zero remainder. For example, think of the number 12. Its factors are 1, 2, 3, 4, 6, and 12. Notice how there's a finite amount of them, and they're usually smaller than the number itself? Now, multiples, on the other hand, they're like the endless footprints you get when you just keep multiplying a number out. So for 12, its multiples are 12, 24, 36, 48, and yeah, they literally go on forever. So just remember, factors break numbers down, while multiples build numbers up. Moving right along to section 2, divisibility cheat codes. Let's be real for a second. Nobody, and I mean nobody, likes doing long division if they don't have to, right? So when you're hunting for factors, you really need some shortcuts. And these rules are basically your ultimate math survival guide. I mean, we all know that numbers ending in 0 or 5 are divisible by 5, and that even numbers are divisible by 2. That's easy. But look at the rule for 9. Want to know if a crazy number like 7,263 is divisible by 9? No calculator needed, just add the digits up. 7 plus 2 plus 6 plus 3 equals 18, and since 18 is divisible by 9, that entire massive number is also divisible by 9. How cool is that? And it works the exact same way for 3. If the sum of the digits is divisible by 3, the whole shebang is divisible by 3. These little hacks are going to save you so much time. Okay, section 3, breaking down prime factorization. Now we get to use those divisibility cheat codes to hunt down the unbreakable atoms of math, prime numbers. These are the absolute indivisible core of number theory. A prime number only has 2 factors, 1 and itself. Think of 2, 3, 5, 7, and 11. You simply cannot break them down any further. Oh, and a super important side note here. Please remember this. 1 is actually not a prime number. Why? Because it only has 1 factor, itself. It needs exactly 2 to be in the prime club. Also, 2 is the only even prime number in existence, because, well, every other even number can obviously be divided by 2. Any number that isn't prime is called a composite number, which just means it's composed of these smaller prime building blocks. So prime factorization is honestly just like extracting a number's DNA. Every single composite number out there is just a specific, unique combination of prime numbers multiplied together. And using a factor tree, we can break down a number step by step until we're left with nothing but those prime atoms. Let's try it with 48. We can split that into 6 times 8. Now, neither of those are prime, so we keep going. 6 splits into 2 times 3. Hey, those are both prime. We circle them. Now let's look at the 8. That splits into 2 times 4. 2 is prime. Circle it. The 4 splits again into 2 times 2. Now I just gather up all your circled prime numbers. It turns out 48 is really just 2 times 2 times 2 times 2 times 3. Or, to write it a bit more elegantly using powers, 2 to the power of 4 times 3. And there you have it, the unique genetic makeup of the number 48. Which brings us to section 4, mastering HCF and LCM. All right, time to upgrade to our heavy-duty power tools. This is where we start comparing the DNA of 2 different numbers to see how they interact. We have 2 powerhouse concepts here, the highest common factor, or HCF, and the lowest common multiple, or LCM. The HCF is the greatest number that divides exactly into your given numbers. Think of it as finding the biggest shared building block. You're going to pull out the HCF whenever you need to group or share things equally. On the flip side, the LCM is the smallest number that is a multiple of your given numbers. It's looking forward into the future, trying to find where the footprints of 2 different numbers first land on the exact same spot. You'll want to use the LCM when you're trying to sync up repeating events. And here is an absolutely amazing visual shortcut for finding both of these at the exact same time, the Venn diagram method. Let's map out the DNA of 24 and 36. So 24 breaks down into 2, 2, 2, and 3. 36 breaks down into 2, 2, 3, and 3. We take their shared factors and place them right in the middle intersection, a 2, and a 3. Then the leftover 2 from 24 goes on the left, and the leftover 3 from 36 goes on the right. Now, here's the magic. If you want the HCF, just multiply the overlapping middle section. 2 times 2 times 3 equals 12. Done! And to find the LCM, you just multiply every single number you see across the entire board. 2 times 2 times 2 times 3 times 3 equals 72. Literally one single diagram, and you get both answers perfectly calculated. It's brilliant. Oh, and I've got to share this quick pro tip with you because it's like a built-in safety net for your math. There's this really beautiful relationship here. If you multiply your two starting numbers together, the result will perfectly equal your HCF multiplied by your LCM. Let's test it on our last example. 24 times 36 equals 864. Okay, now what about our HCF of 12 times our LCM of 72? Yep, also 864. It's a fantastic way to double-check your work and guarantee your answer is solid. Let's put all this into action in Section 5, Solving Real-World Puzzles. The real fun begins when we unleash these theories on some actual real-world boss fights. Let's look at this puzzle right here. A teacher has 24 pencils and 36 erasers, and she wants to distribute them into identical gift packs using every single item. So we have to ask ourselves, because we are dividing items into the greatest number of identical groups, which tool from our kit do we need? Are we building something up or are we breaking something down? You guessed it, because it's all about sharing equally, we absolutely need the highest common factor. We just look at those prime factors of 24 and 36 again. We find those common prime building blocks, the 2, and the 3, to figure out exactly how many identical packs we can put together without having any awkward leftovers. And boom, the math tells us our HCF is 12. That means she can make exactly 12 identical gift packs. And, if you want to take it just one step further to see what's inside, just divide the starting items by 12. 24 pencils divided by 12 packs means 2 pencils per pack. 36 erasers divided by 12 packs means 3 erasers per pack. Perfect, identical distribution, completely solved using number theory. Okay, here's our second puzzle, and this one requires a totally different approach. Imagine 2 bells on different schedules. One rings every 12 minutes, the other every 18 minutes. They just chimed together at exactly 9 a.m. Now, we aren't splitting things up anymore, right? We are looking for the next time these repeating cycles match up in the future. Since we're dealing with recurring timings here, we're going to deploy the lowest common multiple. We need to find the smallest multiple that both 12 and 18 share. By mapping their prime factors and taking the highest power of each, or just by using that trusty Venn diagram method we loved earlier, we can calculate the LCM. And it turns out the smallest number both 12 and 18 multiply evenly into is 36. So 36 minutes is our magic number. Now just add that 36 minutes to our 9 a.m. start time. And we know for sure that those bells will sync up exactly at 9:36 a.m. Seriously, whether you're coordinating bus schedules, setting up repeating alarms, or syncing up flashing lights, the LCM is your master key for timing. Before we officially wrap this up, I want to quickly myth-bust some common traps just one last time. Remember, factors are small, multiples are huge. The number 1 is never, ever a prime number because it doesn't have 2 distinct factors. When you're finding the HCF, you've got to be super strict. Only take the prime factors they explicitly share. But for the LCM, be greedy. Take all the prime factors with the highest powers. If you can avoid those little pitfalls, you're going to navigate these problems flawlessly. Well, look at that. You've just built a seriously powerful mathematical toolkit from absolute scratch. You can now look at a number, extract its prime DNA, and use the HCF and LCM to perfectly organize your resources or sync up future events. It's so much more than just numbers on a page. It's literally the invisible rhythm of the world around us. So the question is, how are you going to use these cheat codes to decode the hidden patterns in your own daily life? Thanks for hanging out with me on this explainer, and keep looking for the structures beneath the surface.